Today's event is being recorded. A link will be shared with you after the webinar is complete via email. We welcome you to revisit the content yourself and share it with your colleagues. The webinar and its contents will also be available via the BlueSpark YouTube channel. All attendees are on listen-only mode, so you'll be muted throughout this webinar. Please have a look at the Q&A box on your screen. If you have any questions for our presenters at any time, please enter it there. Steve Pettin, our Global Sales Director, will be assisting and answering your questions during the Q&A portion at the end of the presentation. Also during the presentation, we will have several polling questions. As a warm-up to get started, pull the first one up right now. What is your favorite color? This is a multiple choice question. Light blue, cyan blue, royal blue, or dark blue? I'll give you a few moments to vote there. We're going to be closing that up. The results are cyan blue and royal blue, which are two of BlueSpark's colors. Sorry. Note that due to the increasing users on many online platforms, you may experience intermittent availability of HD video during the live event. Thank you for taking the time out of your busy schedules to join us today. And I would like to introduce Charles Fensky, whose main focus with BlueSpark Energy is client applications.
Thank you, Stephanie. So what I would like to do today is redo a presentation that I gave at the SPE Formation Damage Conference in Lafayette earlier this year. This presentation relates to unplugging standalone sand screens with high power shockwaves. Before I get started, I would like to thank the contribution of my co-authors. Their insight and contribution was quite wonderful and we all appreciate it. I'd also like to take this moment to thank our sponsoring organizations for the resources and time to share this knowledge with you today. So the objective today is to introduce a new method with high power shockwaves that is cost effective with a simple wireline deployment and a service that requires minimal personnel on site, often only one person. This method is environmentally safe and it doesn't require any use of any chemicals being either brought to well site or having to be managed on that well site. This method also has very low operational risk to sand screens and completions. So now I'd like to share the results of cleaning those sand screens and completions with high power shockwaves. So before we get started, let's have our first poll, please.
Do you have scale issues in your well? Give everybody a few moments to answer.
Hey, Steph, Chuck, Steve here. Hey, I just want to make a comment here. I just got a question about the jerseys that we all have on today. And I just kind of, while people are answering the first question here, and maybe even give some other people, we're kind of just at 11 o'clock, so just give some other people some time to join. Just kind of want to give a little insight on the jerseys and maybe a little bit of insight on the I guess, reasons why we have them. It's been a tradition since day one at BlueSpark as you get hired, new employees. It's kind of a tradition that everyone would get a hockey jersey with their number on them. The number is kind of represented as the employee number that you would have. Hockey, obviously, we're a Canadian company. Hockey's kind of near and dear to all of our hearts, I would say. So that's the idea around that. I mean, it's just more also to say that, hey, we're in a team. Again, as Canadians, we think hockey is the ultimate team sport, and we think BlueSpark is a fantastic team, and we want to make sure that every part of that team member has an important part to play. So that's kind of the idea around the jerseys. I'll throw it back to you, Chuck.
Perfect. You want to go ahead? Okay, so let's start with the basics. Go ahead and talk about our poll.
So I guess I could have done that. I never seen the results. Sorry, Chuck. I'll take that too. So do people have scaled in their wells? 38% say yes, and there's even percentage says they don't know. So for the people to say yes, I think you'll find the rest of this presentation interesting, and we hope to talk to you guys more about it at the end here.
Thank you. So let's look at our problem statement here. So in a well, typically when you have fluids that have ions, produce fluids that either come from the reservoir coming up in a production fashion or being injected down, when those ions go through a change in temperature and pressure, it's not uncommon for them to actually settle out and start accumulating in the well. Sometimes they accumulate right at the perforations themselves, causing impeding of flow. Sometimes they accumulate along the tubing string coming up or the casing, causing a reduction ID. In extreme cases, they can even actually almost block off the flow altogether. This phenomena, although it happens in the casing, this also happens actually in the sand screen itself. So where the normal function of a sand screen relates to actually filtering out the solid formation materials to prevent them from coming in the wellbore. When you actually get scales start forming up inside them, now they can bond together and make a blockage, which can restrict that flow from actually coming into the wellbore. So what I'll show is treat you with a bit of a video right here. So this video is actually an example of a sand screen that was actually pulled from a well where they was having flow issues. This pores and flow paths themselves are plugged with sand, calcium carbonate, and iron oxides. And what we're going to show in this video is using this downhole wasp tool, actually using the pulsing action and observe what happens to the flow paths. So as we do those applications of those high power shock waves, we can see we're breaking up that brittle material and causing what was actually bound together to become free and open. So now let's have a closer look in more detail. So for the screen I showed you before, we have a before picture, which we show the actual brittle material and the fines actually plugging up the flow paths that are in that screen. After the application of shock waves, we can now observe that those flow paths have now been opened up so that now the fluid can actually go through as intended. What's also key about this is, as we observe this fine sand screen inside here, the application of high power shock waves really only affects the brittle materials. The actual ductile materials such as metals are not harmed in this process. In this paper, the key element was we actually took 4 pieces of downhole completions that were recovered to surface. These 4 pieces had different types of scale that were causing blockages in the flow path. And then we used the actual downhole tool to actually apply those high power shock waves to that particular device. And then we measured the resulting opening that occurred from the application of those shock waves. We look at the original case where we have no shock waves applied. We can actually see the flow paths are actually plugged up with scale and debris. And now the successive application of more of those shock waves and pulses causes those flow paths that were plugged to become open and able to flow again. When we looked at these samples, we actually quantified what was actually the plugging material that was closing up those doors, which are preventing things to flow through. It shouldn't come as a surprise that there's lots of sand and actually fines. That's the purpose of the device. But what was also key about what was blocking it up was the accumulation of scales that was holding those blockages together. So in this sample right here, we have examples of calcium carbonate. We have different corrosion-based scales. All of those items which are binding up that material in different concentrations. Let's go ahead and do our next poll question, please.
Which scales are most common in your wells? So this is multiple choice: calcium carbonate, barium sulfate, iron carbonates, iron sulfides, or other. Let's give it a few moments here. Still votes coming in.
No, it's
Okay, so we're going to share some results here.
Hey, Chuck, it looks like a lot of people are struggling with calcium carbonate. And I know from our well data and results that we see calcium carbonate as being a challenge that a lot of our customers face. I know we have lots of case studies and examples of that, as she's shown here. But yeah, calcium carbonate, and then barium sulfate, which is a challenging scale for a lot of people, but that seems to be where people are struggling with today.
That's good, so it aligns. So let's look a little bit further in. So in these samples today, when we pulsed them, we actually took the debris that was actually removed from the scale, from the sand screens, and then looked at it in much better detail to find out what was the mechanism or what was actually going on in this process. What we observed in those brittle scales, such as calcium carbonate and barium sulfate, is when you apply those high power shock waves, it tends to generate micro cracks and fractures in the scale itself, really debonding and breaking it apart. So you can see that here in the images in the middle, where it affects both the brittle scales related that are iron-based, and also in this case, the brittle scales that were related to the calcium-based as well. When we looked at other samples that were recovered from this pulsing, and we look into them in much more detail, we also observed some other interesting phenomena. We observed that in that aggregate of material, we're actually causing cracks to form in the boundary between the different materials. And also in the brittle materials themselves, you can see those micro cracks growing. What's unique about this is that we tend to break up the scale and debris, the scale particular, that brittle scale, but the actual sand and the formation pieces are not harmed. So that way you can actually unplug the blockages and cause the device to work as it was intended to. So in this paper, we also went through several different case studies. I'm going to hit on a couple key ones here. The first one, which is key, relates to calcium carbonate scale. But what's key about this one, it actually relates to two problems in the same well. We have the original problem related to scale accumulation in the casing itself, and a secondary problem related to scale accumulation in the perforations as well. So when we use the high power shockwave tool in the casing, initially we could see the scale accumulation from the ID of the casing growing in. And then after the application of high power shockwaves, we can see that that brittle scale has now been broken away and the ID has been returned back to its original state. What's unique about these shockwaves is that although they actually clean right to the interface of wherever the scale is, so if there was a crevice or a gap, they can actually penetrate into there, which is something that's a bit more challenging for other devices. To that end, when I have a perforation and I'm able to actually cause the pulsing going in, I can actually remove the scale from that perforation. And in this case, you can see an increase in production related from 4.8 to 8.5 barrels per day, once that blockages or that door was open, which allowed that flow to actually come through. Our next case study I'm going to hit on really relates to actually barium sulfate scale for 9 wells in Texas. As many can attest, barium sulfate scale is not an easy one to manage. So over this aggregate of 9 wells, we observed a 45% increase in oil production and a 72% increase in gas production, but we saw a decrease in water cut. What's special about this is when you apply those high power shock waves, they're very localized. So you can actually target places in the well where you want the fluid to flow to increase, by the same token, not actually target places in the well where you don't want actually fluid to go through. And that's something very unique about this application, being able to choose where you want the application to take place. So here I'm showing a summary of the case studies that went into in much more detail in the paper. I want to hit on a few key themes to reinforce. One is that where the challenge was related to a brittle scale accumulation in the well, where that brittle scale was causing a flow impediment, once that brittle scale was removed, that flow can actually resume again. Likewise, because it can do multiple things in the same well, where there was actually scale needed to be removed from a downhole subsurface safety valve that was affecting its operational sealing, or whether that be a gas lift valve where it's actually flow ports are actually being plugged up, or you can't actually get into the profile to actually get it removed. This generic approach actually works for any brittle scale. We've used it in offshore and land wells. We've used it in vertical wells, deviated wells, horizontal wells around the world. The other thing which is key about this technology relates to actually its very small footprint and there's many things it can do. So it's often well suited for light well intervention vessels, where now you can have a device which can actually clean up some features in the well, clean up some perforations, and also remove scale, all requiring just that one simple wireline tool and a single personnel on board. So let's go ahead and have our next poll, please.
Okay, so which items would you consider using shockwaves to clean scale from? Sand screens, frac packs, slotted liners, tubing, casing, subsurface safety valves, gas lift valves, nipple profiles or other ID restrictions, or other?
Not sure what other there would be in a wellbore, Steph, after that list we put together there.
Okay, we still got a few votes coming in. We're at about 43%. Give everybody a few more minutes.
Hey, while we're waiting, I'm getting some questions coming in here, and I need to be completely honest with the group. I think I've attempted to answer some of them, but I think they've gone into the unknown. So after the end here, Chuck and I will do our best to answer them. So they're not being ignored. I see them. I'm just trying to figure out exactly how to answer them live here.
Thanks, Steve.
Okay, so we're going to close up the polling here. And there's your polling results.
Hey, Chuck, it looks like the production optimization from screens is important, frac packs as well. And then down probably, then it's an even between complex completions equipment like SSVs and GLVs.
I think what impresses me is just that breadth of list of all the different things it can do. Yeah.
Agreed.
All right. So, in conclusion, high power shockwaves have the ability to break up brittle scales. This application of high power shockwaves doesn't harm the ductile completion equipment. And this method is effective for many different items in the well, whether that be removing things from the ID or actually in the intricacies of the screen itself. And it really is a solution where the challenge is brittle scales. So our final poll, please.
Do you think cleaning scale with shockwaves is a technique that you would consider in the future? We still have some votes coming in.
I'm hoping everyone says yes to this one.
We believe in it.
Okay. Yeah. And there you go, Steve.
Hey.
All right. So now, all right, we really appreciate your precipitation. So now I'd like to transition into the question and answer session. If you please, as Steve mentioned before, please enter your questions in the chat box. Likewise, if you have any additional questions or feedback, please feel free to email us at webinar@bluesparkenergy.com. Get a hold of myself, Charles Fensky, or our sales director, Steve Petton. So with that, I'd like to open up the question and answer session. Go ahead, Steve.
Thanks, Chuck. Again, it was an awesome presentation. Appreciate yours and Stephanie's effort in getting this organized today. There were 5 questions that came in as we were going here. So I will start. I'll go through some of these. So are the results fluid dependent? Chuck, I'll throw that one at you. And I think what we're being asked here is, will this work with oil? Will it work with water? Are we particular on the fluid that's going to be in the wellbore when we're treating it?
It's a good question. So I'll dive into a little bit of the physics of how it works. So we have showed you that wireline tool earlier. You also notice that when we're doing, we're actually has to be in a fluid so that shockwave can actually transmit away from the tool and actually get to the scale or the item that needs to be cleaned. So wherever the application of high power shockwaves is going to be needed, in that particular location, you have to be in fluid. Fortunately, we don't discriminate what kind of fluid it is, as long as like it's water or an oil. Unfortunately, if it can't be gas, just like you'd have in your car where you have a shock absorber absorbing that shock. If you have a gas at the point of treatment, this won't work. That being said, we've had some innovative solutions that actually allow the tool to actually have a device that can temporarily retain fluid, such that even if you don't actually have fluid at the zone of treatment, you have a way of actually helping do that. Does that capture the question, Steve?
I think I think that answers it for me. On that, then I'll just roll into this one here from that's asked, why doesn't the pulse damage the sand screen? Sand screens are pretty pliable, easy, soft material. Why don't we damage those?
So I think that's the key. And so the item you have to look at is there's 2 different types of material. You have a brittle material. When it actually sees a wave, it actually can't absorb that energy and it'll actually crack and break. Where you actually have a ductile or more elastic type material, it can actually absorb that energy over a period of time before it breaks. The other key thing about these shock waves is they happen in very, very small amounts of time. So you'll get that burst, but only lasts for a few microseconds and then it's gone again. So that ductile material, such as the metal, can absorb this without actually deforming or having any issue.
Again, thanks, Chuck, and thanks again for all the questions that are coming in here. I'll take this one. How many wells Blue Spark completed? Just got an update on that this morning, actually, from our data manager, Mike. It's 550 so far that we've completed globally. Many different applications. Chuck focused today on sand screens and production improvement and optimization. But again, there's been lots of SSVs, tubing cleaning, etc. On that, then, Stuart asked, have we ever considered using the WASP in surface line blockages and not just wells? And we get this a lot. Whenever we present this technology, we get lots of questions around what if, how could we do other applications? I think the answer to that is if we can get the tool safely into these surface lines and there's a liquid medium there, then absolutely it's something that we could consider and look at. Here's one for you, Chuck. Does that mean, I guess with your answer of brittle materials, does that mean that it does or doesn't work on soft materials like wax, paraffin, asphaltenes?
That's one of the challenges you can imagine. If you were to take a rubber hammer and smack something soft and like a rubber mallet, the hammer hitting rubber, that rubber would absorb it and it would actually cause it to deform. So that is true that we're not going to have that effectiveness in those type items. Yeah. Yeah.
Okay. One other here. Chuck, just go into how many pulses we can do per run and maybe even expand out a little bit about how many pulses potentially are even required for different applications that we'd be treating.
So the WASP tool comes in two basic configurations. One configuration, the standard one, can do about 3,000 pulses per run. The extended life version of the 6,000 pulse tool can do 6,000 pulses per run. When we're pulsing, it is dependent a bit on material. What we've experimentally observed is that where the materials are related to precipitate scales such as calcium carbonate or barium sulfate, they tend to break up easier. Where we have scales that are more corrosion based, such as actually iron sulfates or iron oxides, those tend to actually take more. So in situations where it's where you don't actually know what you do, we tend to default at approximately 200 pulses per meter. That being said, as you get more information of the well, we can actually plan to optimize that accordingly.
That's awesome. Got a question here from a very smart guy, I know for sure. What is the preferred well conditions for deploying the tool? Flowing while pulsing, pulsing in static conditions, pulsing while injecting? Why and what typically has the best results?
Okay, so I'm going to break it down into bitty pieces. So the first thing we need to consider is we have to be able to get that shock wave to wherever it happens to be. So as I mentioned before, gas absorbs shock waves. So that media between having the least amount of gas possible, ideally none, is optimal for getting that to transmit over. The next part of the equation relates to once you actually break it up, now you look at actually the transportation. So typically when it breaks off the wall, in a vertical well or where there's reasonable deviation, it'll fall and bring it away. So if there's much material going by, you may actually get some hydrotransport type effects actually flushing it along. That being said, likewise, sometimes you can actually get some assist from the reservoir. So let's suppose I have a blockage, so I have pressure 1 and pressure 2. When I start cracking that door, as you can imagine, that pressure assist can actually cause some of that stuff to break out freer and make its way further. Likewise, unfortunately, the opposite is also true. If I have a heavy overbalance, it may push the other way. So those are some of the factors you can consider of actually how to work it from there. But really, you have to look at the application of what you're trying to do and the variables that constrain you.
Thanks, Chuck. Let me see. I've got one more question. I'm not sure if there's anyone else. Oh, there's some more coming in here. What are the most significant risk and consequences associated with the operation? That's a good question. We get this a lot in a lot of the applications we've been talking to customers with, and the minimal risk that's associated with deploying our tool is one of the reasons why we feel we've had such great success in the last short period of time. So Chuck, what's some of the risk that we see that our customers have kind of maybe suggested to us?
So one of the risks is, as you can imagine, we're going into wells that have scale and ID changes. So one of the ways we minimize that risk of having a very slick tool such that there's nothing to hang up or grab. So if we can actually get down and get through, we can actually work ourselves accordingly. Some of the other risks relate to is really the unknown. One of the, so we go through a very detailed pre-job planning to actually reduce that risk, to mention some things that we actually do have food we're going to be treating. We actually do not have gas where we don't want it to be. So some of those things that we actually work out is mitigating the risk. One of the other key variables about this is our energy level. As you can imagine, we've actually have a very tuned product for the oil field application such that we can actually make sufficient output to break up those brittle scales, but we're not having ludicrous amounts that could actually cause metal to implode. So that's another thing it's worked into it. It's a device that's set up in such a way that we're not going to do any harm. In reality, either we'll do something or nothing. Yeah.
Yeah, I know. It's kind of an odd answer that when I get this sometimes, it's the biggest risk outside of the, you know, same as if you were deploying a production logging tool. I mean, we have a slick body tool, so the chances of getting stuck are minimal. The pulsing's happening at the bottom of the tool, so the debris is kind of falling down. But yeah, because of the way the low energy that we're using, again, just to reiterate, the worst thing that could happen is that we have a minimal to no effect on anything that happens in your well. And I'm not exactly sure what else we can do in the oil and gas industry when you're running something that you have a minimal risk.
Well, I think the other thing is key is that this really works really well on scale. It doesn't fix a broken control line. It doesn't fix a zone that has no reservoir drive anymore. It's really good at getting rid of scale. Yeah.
Okay, now the questions are coming in fast. Let me just kind of, sorry about this, just real quick. Any plans, Chuck, for a 15K rated tool? I think this is coming from a customer in the Gulf of Mexico.
Yeah. So I think what we like about this application is each time we do this, we get more and more interest. So although we made our original profile to handle 10K and 130 degrees Celsius, we're getting more and more applications and challenges to push ourselves forward. And that's something we're looking to enhancing and improving as we go.
Okay, I think we've answered this one. What is the distance? Okay, nope, this is a different one. What is the distance that the shockwave can travel from the well? Where are you in your research point? So I think some of these, I think I'm going to reply to this, and this is an anonymous attendee. I don't know if you want to take this with Chuck. I mean, there's some science we have and we can share with these.
I think the other thing to keep in mind is we're unfortunately still constrained by the laws of physics. So as you can imagine, we have a point source. As that point source makes the shock wave, as it grows away from it, its amplitude decreases. So there's no doubt that that wave can travel a long ways away from the wellbore. The challenge is as it travels away, does it have sufficient energy and output to actually cause that brittle material to break? And I think that's the key part. So for, as you can imagine, for wellbore applications on the IDs of tubing or on the IDs of casing, that would definitely, it works extremely well. If you could imagine trying to have enough amplitude many kilometers away, I don't believe that it would do that. So.
Okay. That's what we have for questions. I'll give it a couple, I'll just say a couple more thank yous, but if there's any other questions, please direct them to the webinar at bluesparkenergy.com, myself, S.Penton at bluesparkenergy.com, or Chuck at c.finsky at bluesparkenergy.com. But again, I want to thank everyone. I want to thank for joining. I want to thank Chuck and Stephanie for helping me host this today. And again, we look forward to talking to you guys. We'll send a follow-up link to this presentation. Please feel free to share it with any of your colleagues that would be interested. And again, thanks a bunch. Chuck, is there anything you want to say?
No, thanks again for your and Stephanie's help, and I hope this was informative today.
Thanks, everyone.